Now that we have determined our first cell height using the Y+ study, we can then perform a mesh study by halving the mesh and monitoring CL and CD. We can then graph the results and make a decision about the appropriate mesh size for the 3D simulation. First, let's duplicate the first simulation and clear the generated mesh. For this simulation, let's halve the face size. It was found that the edge sizing wasn't necessary. Now adjust the face size to 100 mm and keep the body of influence for all simulations at around 10 mm. Generate and check the mesh quality and resolving it to the best of your ability if there are any issues. Adjust the edge sizing around the outer domain for a smooth transition. For this simulation, 25 divisions at the inlet and above the fairing worked, 60 elements in the wake, and 50 elements towards the outlet. After the mesh has been created, generate and update the workbench and enter the setup. While running the simulation, it was found that clicking curvature control on the K-Omega SST turbulence model helped resolve the wake. As the setup should be ready, initiate the run and run the simulation, checking to make sure that the monitor points and residuals have converged. After the solution has been run, it's always a good idea to go back and check the results. After the results have been checked, duplicate the simulation and half the face sizing and run the simulation again. Now during the fourth mesh size, where the mesh size was 25 mm, there were convergence issues arising. The current number under solution controls is used to determine the time step each iteration will take. If the time step is too large, Fluent will have issues capturing the flow. If the time step is too small, it will capture the flow but may take too long. So start off with the default value of 200 and half the current number if issues arise. 4 different meshes were required to find a solution that was mesh independent. The results of each of the simulations can be compared next to each other by dragging the solution into a single results tab. The mesh of the first and last simulation can be seen. Now overlapping them shows the difference in mesh density and why the contours and coefficients will be different. Now in our first run, the outline of the wake is jagged due to the large mesh size, but is captured as the mesh density increases. Now looking at the flow structure inside the wake, as the mesh density increases, the resolution of the wake structure increases, with the finer mesh capturing the recirculation region. The turbulent kinetic energy within the wake also looks constant after the third mesh, showing the same intensity and shape. The results from the simulations can be viewed in the parameter set. They were then put into Excel and a table created, comparing the successive sizes to one another. The simulations showed that there was less than a 1% change in CL and CD from mesh 3 to 4, showing grid convergence, which will be used in 3D.